Hey folks, the next thing we're going to look at is how to solve oblique triangles, which is going to require us to look at the law of sines and then the law of cosines. So the law of sines, the first thing that I'd remind us of is if we're giving a right triangle, we know how to solve a right triangle by using right triangle trig, SOHCAHTOA. Remember, sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So that's how we can solve right triangles. They're the friendly triangles. However, if we have an oblique triangle, and an oblique triangle, oblique is a fancy way of saying the triangle is not a right triangle. So if we have an oblique triangle, we're going to solve that triangle, an oblique triangle, by using the law of sines or possibly the law of cosines. So I thought I would kind of summarize the information here real quickly. In this video we're going to be dealing with the law of sines. So if the information we are given, if we know from the given information two angles of the triangle and any side. So we know two angles and any side. You may remember from geometry that's called the angle-angle side or angle-side-angle case. Or if we're given two sides and the measurement of an angle, and the angle's opposite one of those sides. You may remember from geometry that was called the side-side angle case. Given those two situations, we're going to have to use the law of sines in order to solve the triangle. Quick review on solving a triangle. Remember, to solve a triangle, that means you need to find the measurement of all three angles and the lengths of all three sides. So there's 6 bits of information that you have to know in order to have the triangle solved. However, if the information you're given for your oblique triangle is the measurement of all three sides, side-side-side case, or you're given the measurement of two sides and the included angle, the side-angle-side case, in these situations here, we're going to start off by using what's called the law of cosines. Now, law of cosines I'll look at in the next video. In this video, we are going to be dealing exclusively with the law of sines. So to recap, right triangle, use SOHCAHTOA. Oblique triangle, a non-right triangle, we're going to have to use law of sines or law of cosines. I would suggest you kind of know these situations, but I think if we do some examples, it becomes evident how to attack a problem. All right, hey, here's your law of sines for a triangle that I just call ABC, where the lengths of the sides are ABC. A over the sine of A, so that's side A over the sine of angle A, equals B over sine B equals C over sine C. Or equivalently, I could look at it as sine of angle A over side A equals sine of B over little b equals sine of C over little c. I generally will draw an oblique triangle. I'm going to sketch an oblique triangle like in this first example I'm going to do. I just kind of make all my triangles look the same. I don't try to draw it to scale. I'm not going to pull out a protractor and try to be precise with my graph. I'm just using the graph of any triangle that I put up here just to kind of see a picture and organize my information. Just one thing that I will remind you of, that I labeled my angles A, B, and C, and by doing that, just kind of remember the side that is opposite angle A will be measurement little a. That's side little a. The angle opposite angle B is little b, and the side opposite angle C is little c. So once you label your angles, the sides opposite of those angles would be the lowercase sides. Here in this first example, let's solve the triangle where angle B is 52 degrees, angle C is 29 degrees, and side A is 43 centimeters. Okay, the first thing I would do is I'm going to sketch a triangle. And as promised, all my triangles they're going to kind of look the same. This is angle A, angle B, angle C. Now I'm going to put into my triangle at this point, I'm going to put into it the information that I was given. So I know angle B is 52 degrees, so I'll put 52 degrees there. Angle C is 29 degrees. And side A, that would be this side here, is 43 centimeters. So here's side C, here's side B. And I even go a step further, and this is going to pay off when we get to the supposed ambiguous case of the law of sines. I like to organize my information. So usually after I sketch my triangle and put in the given information, I'll come over here to the side and I'll put just angle A, angle B, angle C, side A, side B, and side C. You know, to solve the triangle, I have to know the measurement of all three angles and the measurement of all three sides. Put in the information that I was given. I was given angle B is 52 degrees, angle C is 29 degrees, and side A is 43 centimeters. So I already know 3 of the 6 bits of information that I need to have determined in order to solve the triangle. So my game now, my task at hand, is I have to find the measurement of angle A, the length of side B, and the length of side C to have this triangle solved. Probably the first thing that I would find, I'm not going to write this down, I'm just going to, verbalize it. Probably the first thing I'd find is the easiest thing to find. It's the measurement of angle A. I mean, please remember that in a triangle, the measurement of the 3 angles, if you add them up, it has to add up to 180 degrees. So angle A plus angle B plus angle C has to be 180 degrees. So I would just simply add angle B and angle C together, and if I add those up, I think I get 81 degrees, and I would subtract that from 180 to get the measurement of angle A is 99 degrees. And see, that doesn't require law of sines, law of cosines. It doesn't require anything other than knowing that the 3 angles of a triangle add up to 180 degrees. All right, now check it out. I still need to find side B, and I still need to find side C. Since it's an oblique triangle, this is where the power of the law of sines come in. And I have over here like the 2 different versions of the law of sines, and I will be using like the first version, and I'll show you why. Let's find side B. So to find side B, I'll just make that note right here. I'm finding side B. What I'm going to do is I'm going to use the version of the law of sines where what it is I'm trying to find, side B, is in the numerator. Because that's going to save me 1 step of algebra. And hey, I'm all about saving steps of algebra whenever I can. So when I look at this, I would start off by saying, well, B, side B, over the sine of angle B. Well, I know angle B is 52 degrees, equals, and this is the key. I know angle A, and I know the side opposite angle A. So I will write the fraction A over sine of A. So I have B over the sine of 52 degrees equals little a, which is 43, over the sine of angle A. So that's the sine of 99 degrees. And what I would do next, I would multiply both sides of this equation by the sine of 52 degrees. Then I'm going to use my calculator. And notice these angles are in degrees, so please make sure your calculator is in degree mode. I will get angle B to be pretty close to, I'll get side B to be pretty close to 34 centimeters. So I know side B is 34 centimeters. Put a little break here. All that's left is to find side C. So to find side C, that's what I'm trying to find. I'm going to put that in the numerator of a fraction. So C over the sine of angle C. So that's C over the sine of 29 degrees equals, and I'll use the A's again, side A over the sine of angle A. And just like what I would do here, my first step in solving here would be just to multiply both sides of the equation by the sine of 29 degrees. And then I'd use my calculator, 43 times the sine of 29 degrees, and then divided by the sine of 99 degrees. And I would get side C to be pretty close to 21 centimeters. So let me put that here. I kind of call this my solution area. I have solved the triangle. And I'll do one more thing. It doesn't guarantee that my answers are correct. It just guarantees that my answers are reasonable, that they're making sense. Look at the largest angle. Largest angle is angle A. The side that is opposite the largest angle, that would be side A, better be the longest side. And 43 centimeters, that is the longest side. Find the smallest angle in here, 29 degrees. The side opposite the smallest angle better be the shortest side. And it is. 21 centimeters is the smallest side. And again, it doesn't guarantee that my answers are absolutely perfectly correct, but it does tell me that my answers are reasonable. So that's a first example of using the law of sines to solve an oblique triangle. All right, hey, next up, here it is. It's what a lot of books and people refer to as the ambiguous case of the law of sines. And you would probably see in your textbook, many pictures of triangles that would fit into this ambiguous case of the law of sines. To cut to the chase, the ambiguous case is the side-side angle case. In the side-side angle case, the information that you are given, the given information can do one of three things. The given information can either produce 0 triangles, 1 triangle, or 2 triangles. And that's why it's called the ambiguous case, is that from the given information, you really don't know what's going on right away. You don't know if there's 0, 1, or 2 triangles. I don't really think it's that ambiguous of a case as long as we remember how to solve trig equations and the unit circle. It's all going to come back to that, and it's going to remove this ambiguity from the supposed ambiguous case of the law of sines. Here, we'll look at an example and I'll show you what I mean. All right, hey, let's check out this example. This example says, solve the triangle, and what we're given is angle A is 70.1 degrees, side A is 21.5, and side B is 29.3. I've already taken the liberty to have my triangle sketched in here, and again, notice all my oblique triangles look the same, big deal. I labeled the given information, and what I need to do now is fill in into this area, what I know. This is like my quote solution area. Okay, so again, remember, to solve a triangle, you need to find the lengths of all 3 sides and the measure of all 3 angles. So that's what we have. That's what we know. Now check it out. This is what's called as the side-side angle case. This is what the book is going to say, or any book is going to say, is the ambiguous case. This is what tells me that I have to worry about 0, 1, or 2 triangles. Look at my solution area. I have no choice. There's absolutely no choice whatsoever in what I have to find first. It's not possible for me to find side C because I don't know angle C. Likewise, it's not possible for me to find angle C because I don't know side C. I only have one choice here. I have to find angle B first using the law of sines. And to me, that's the key to the ambiguous case. Then that's what sets off the warning in my head, 0, 1, or 2 triangles. If I am forced to find an angle first using the law of sines, I get worried. Are there 0, 1, 2 triangles? I don't know. But I attack the problem now. I have to find angle B first. So here we go. Find angle B, and I have to use the law of sines. And this will be the last example where I keep the law of sines up on the board because I'm going to need this space, here in a minute. But the reason why I kept it up here is I'm using this alternate version of the law of sines now. I'm trying to find an angle. So since that's what I'm trying to find, I'm going to be putting the sine of the angle in the numerator. So I would have the sine of angle B over side B, 29.3, equals the sine of angle A, so it's the sine of 70.1 degrees, over side A, 21.5. Now what I would do is I would, just like in the other example, I would multiply both sides of the equation here by 29.3. So that will give me the sine of B is 29.3 times the sine of 70.1 degrees over 21.5. And let me just kind of pull this up here. I have the sine of angle B equals, and now I use my calculator, and I do 29.3 times the sine of 70.1 degrees, my calculator's in degree mode, divided by 21.5. And if I do that, I'm going to write down the number that it gives me. It gives me a number pretty close to 1.2814. This brings me back to solving trig equations. And as I said, there's really going to be nothing ambiguous about the ambiguous case of the law of sines if you remember how to solve trig equations and you remember the unit circle. Look at this. Sine of B equals 1.2814. That's a number larger than 1. Can sine ever kick out a result larger than 1? Absolutely not. So this equation doesn't have a solution. There is no B that makes this true. This equation has no solution. If this equation has no solution, that means there's no angle B that will make this a true statement. If there's no angle B, that means there's nothing for me to put in here. That tells me that my given information is producing 0 triangles. There's no triangle here. No triangle. For the given information, we can't make a triangle. I mean, if you have a protractor and you want to try to sketch this out, you'd see why. But I think the book would have some pictures in there to illustrate it. So right now we've seen in this supposed ambiguous case how to know if you have 0 triangles. Basically, you just start solving, and if you get a number here that's more than 1, you know the equation has no solution. No solution, no triangles. Let's look at another example. All right, hey, here in this example, we're going to try to solve the triangle where our given information is angle A is 29.7 degrees, side A is 27.2, side B is 41.5. Quickly sketched the triangle and labeled the information I was given. Put side C here. And I made my solution area over here and substituted in, the given information. Again, check it out. From my solution area, I can see right now, I have no choice. I have to find angle B first. It's the only option I have is to find angle B. And I have to use the law of sines. So again, I have to find an angle first using the law of sines. I get worried. 0, 1, or 2 triangles are possible now. But I proceed as I did before. So here I go, finding angle B. And I have the sine of B over 41.5 equals the sine of A, sine of 29.7 degrees, over side A, 27.2. Okay, now I would multiply both sides by 41.5. This is the key. This is the key to any of these problems dealing with the supposed ambiguous case of the law of sines. Multiply both sides by 41.5 and then see what kind of number this gives you. So, do 41.5, on my calculator I'd be doing 41.5 times the sine of 29.7 degrees divided by 27.2. And that's going to give me the following number. Pretty close to 0.7559. Alright, so hey, at this point I know I have at least one triangle. The key is seeing what this number is. Remember, if this number is more than 1, I'm done. No solution, no triangle. But this number is less than 1. So I know there's at least one triangle. There is at least one angle B that will make this a true statement. Well, how do I find that angle B? That's right, angle finder. Use inverse sine. Angle B will be the inverse sine of 0.7559. And you should get angle B to be pretty close. I'll just round it to the nearest tenth. 49.1 degrees. So I know right now I could put a 49.1 degrees in here. But now remember, I was forced to find angle B first. That means there's 0, 1, or 2 triangles. Right here I knew 0 was eliminated and there was at least 1. Could there be a second triangle for that given information? Well, yes, there could be a second triangle for that given information. If you think back to the unit circle, this is a y coordinate on the unit circle. The y value is 0.7559. You just found the angle to be 49.1 degrees. Remember, on the unit circle, there are 2 points on the unit circle that would have a y coordinate of 0.7559. One of those points living in quadrant 1, there's the angle that puts us in quadrant 1. The other is living in quadrant 2. But if you remember back to when we solved trig equations, how do you get that measurement in quadrant 2? You take 180 degrees minus this. So my other candidate for angle B is 180 degrees minus 49.1 degrees. It's 180 degrees minus this. So let me write that down. 180 degrees minus 49.1 degrees. And that gives 130.9 degrees. Alright, so now how do I know if the given information has given me 1 or 2 triangles? Well, we know it's got at least one with an angle B of 49.1 degrees. So it has at least one where angle B is 49.1 degrees. But look at this. What if I put 130.9 degrees in for angle B? Would there be another triangle? Yes, there would be. And this is the key part. If the second candidate for angle B plus the given angle, and here the given angle is angle A. So if the second candidate plus the given angle, if that adds up to less than 180 degrees, you have 2 triangles. And notice 130.9 degrees plus the given angle, 29.7, that sum is definitely less than 180 degrees. So we have 2 triangles. This given information is producing 2 triangles. So I'm going to come over here and modify my solution area just a little bit. I'm going to say this is the area for triangle 1. Let me put a line here. And let's write a solution area for triangle 2. But notice in triangle 2, it's going to have the same given information. 27.2, B is 41.5. So both triangles have the same given information. It's just that triangle 2's angle B would be a measurement of 130.9 degrees. So we have 2 triangles here we have to solve. Notice on both triangles it would be easy now to find the measurement of angle C. Add A and B and subtract from 180. So if you add A and B and you subtract from 180, up here you're going to get angle C to be 101.2 degrees. And here you're going to get angle C to be 19.4 degrees. So all that's left in each of these is to find the measurement of side C. Well, how are you going to find the measurement of side C? You're going to use the law of sines. And let's see here. For triangle 1, to find side C, just kind of try to squeeze it in there. You'd have C over the sine of 101.2 degrees equals 27.2 over the sine of 29.7 degrees. And multiply both sides of the equation by the sine of 101.2 degrees. You get C to be pretty close to 53.9. So I'll put 53.9 in there. For triangle 2, to find side C, well, you would have C over the sine of 19.4 degrees is equal to 27.2 over the sine of 29.7 degrees. Multiply both sides by the sine of 19.4 degrees, and you're going to get C to be pretty close to 18.2. So let me put 18.2 in here. Reasonability check. Triangle 1, largest angle, and that is the longest side, the side opposite. The smallest angle is 29.7 degrees. The side opposite is the smallest side. In triangle 2, the largest angle is B. It's 130.9 degrees. Notice side B is the longest side. And the smallest angle is angle C, 19.4 degrees. And 18.2, side C, that is the smallest side. So at least my answers seem reasonable. So to recap here, we've looked at so far with the supposed ambiguous case, we've seen what produces zero triangles, and now you see what, how to attack it if you're going to have two triangles. And keep in mind, I think this is like the key line initially. Seeing sine of B equals whatever this number is. Remember, if this number is more than 1, like the last example, there are no triangles. Numbers less than 1, I know we have at least one triangle. And we find the angle, and then you find the other candidate for the angle, doing 180 degrees minus what you just found. And if this other candidate plus the given angle, if it's less than 180, two triangles. If this happened to be, if you get an angle here, the other candidate for angle B, if that angle plus the given angle, if it happened to be more than 180 degrees, then there's only one triangle, and it would have been for this. So that's a quick recap of, we looked at a couple of examples of the ambiguous case, the law of sines. Hopefully it doesn't seem all that ambiguous. The key is solving trig equations and knowledge of the unit circle. And we're going to finish off this section with a quick look at this law of sine stuff. Quick look at like some applications. All right, I thought we'd look at something that might be kind of new to you. It deals with bearings. There are actually two ways to do bearings. One way of doing a bearing is you're just simply given a single angle measurement, and it's measured from due north. It's measured clockwise from due north. The other way, and this is probably the more common way, is you're given an angle that is east or west of a north-south line. For example, that would be a bearing. That's telling you a bearing. I read this as north 30 degrees west. Some people read it as 30 degrees west of north. It doesn't matter how you read it. I'm happy either way. I read it as north 30 degrees west. What it tells me to do is, I always create like a little template, a little directional template. There's my north-south line, and then I have to know what west and east would be. So I make my like little compass, if you will, north, south, east, west. North 30 degrees west, it just really means, how I interpret it, is I start at north, and now I go 30 degrees towards west. Well, here's west. So I come 30 degrees this way, and let me put a 30 degrees in here. And that's a bearing of north 30 degrees west. Let's look at another one here real quick. Another quick for example. North-south. Let me get my little compass template in here. And now I'll sketch a bearing. Now how would I write that down? I mean, almost all the time you're going to be given the bearing and you have to do the sketch. I just thought I would turn it around here real quick. Well, doesn't it look like that I was starting at south and then I went 30 degrees towards the east? So I started at south and I went 30 degrees towards the east. So this bearing is south 30 degrees east. So to kind of recap, the general form that you are going to be seeing for these bearing problems, these bearing applications, is you're going to see a north or a south. And then you're going to be given an angle theta. And then you're going to see an east or a west. And in this form, this angle theta, it will always be an acute angle. It will always be an angle between 0 and 90 degrees. Think about why. We're going to do an example now. I'm probably just going to pick one from your book to do, and we can see what's happening, what the deal is. All right, I thought we would just do one of them from the book. So, at this point in time, if you need to open up your ebook, I'm going to be doing in section 4.1, I'm going to be doing number 24. So if you want to fire up the ebook and read number 24, or keep it open off to the side so you can constantly look at it, I would suggest you do that now. So if you have to, pause the video and read number 24. Here's what 24 says. You have a forest fire lookout station Alpha, and it's located 20 miles due west of lookout station Beta. The bearing of a fire from station Alpha is south 11 degrees west. The bearing of the fire from station Beta is south 29 degrees west. Our task is to determine the distance from the fire to both lookout stations. And it says round to the nearest tenth of a mile. So I think the most difficult thing to do here is for the given words is to draw a picture, to sketch what's happening. So, Forest Fire Lookout Station Alpha is located 20 miles due west of Lookout Station Beta. That's where I'll start. Here's Beta. And this is Alpha. Alpha is 20 miles due west of Beta. So that means it's on that line there. And I know that this measurement here is 20 miles. All right, so let me come back and read here. The bearing of a fire from station Alpha is south 11 degrees west. So I stop. Here's Alpha. I see a fire south 11 degrees west. So where Alpha is located, what I do is I just lightly sketch in my north, south, east, west template to help me locate where this fire is. So it said the fire's at south 11 degrees west. So that means I start at south, I go 11 degrees towards west, and here's where the fire is. So I'll just write the word fire. But this little angle right here is 11 degrees, south 11 degrees towards the west. Now beta, the bearing of the fire from station beta is south 29 degrees west. So I come over here to beta, and again I sketch in, I lightly sketch in a north-south, east-west template. And I know the fire from beta, lookout station beta, is south 29 degrees west. So I start at south. I come 29 degrees towards the west. And there's the fire. Yeah, it sees the fire. That's 29 degrees there. South, 29 degrees towards the west. So we're being asked to find the distance of the fire from each one of these lookout stations. Well, let me call this side B, and let me call this side A. Lack of creativity. Alpha, the side opposite of that A. Beta, the side opposite of that B. Well, we see a triangle here. We should be able to solve this triangle. But I have to figure out some stuff here in solving the triangle. So let me, oh boy, let me get my kind of reddish colored chalk. Hopefully it'll show up. I need to determine this angle measurement here. Well, that's a right angle. The angle from south to west, I mean, that's a right angle. It's a 90-degree measurement. So this angle measurement here has to be the complement of 29 degrees. Well, that angle, the complement of 29 degrees, is 61 degrees. Well, let's look at this angle right here. This angle. Again, notice I have my template in here, my north, south, east, west template. So I know this piece of the angle is 90 degrees. So it should be 90 degrees plus that 11 degrees. So that gives me that this angle measurement here is 90 degrees plus 11 degrees. That's 101 degrees. So let me put that in, 101 degrees. Well, if this angle is 101 degrees, and this angle here is 61 degrees, to get the measurement of this angle, I'm just going to add those two together and subtract from 180. And that gives me this angle down here is 18 degrees. Now we see a classic law of sines application. I have to find the length of B, the length of A. I have to find side B and side A. So let's come over here to the side. Let's find side A. And notice side A, side A of this triangle is the distance from lookout station beta to the fire. So to find side A, using the law of sines, I would have A over the angle that's opposite it. So A over the sine of 101 degrees equals, and now look, I know this angle and the side opposite is 20 miles. So it would be 20 over the sine of 18 degrees. So 20 over the sine of 18 degrees. And again, if I use my calculator, make sure my calculator is still in degree mode, multiply both sides by the sine of 101 degrees, I get A to be, well, the book said to round it to the nearest tenth, so 63.5 miles. So the distance from beta, lookout station beta to the fire, that distance is 63.5 miles. To get side B, which is the distance from alpha to the fire, well, I'm going to use the law of sines again. B, so I have B over the sine of 61 degrees. So B over the sine of 61 degrees equals 20 over the sine of 18 degrees. And again, folks, just multiply both sides by the sine of 61 degrees, and we get B to be about 56.6 miles. And let's look at an example of looking at an application where we got to use the law of sines, and it incorporated a little bit of new information, this bearings concept. Most difficult part will probably be sketching the picture. But take your time with sketching the picture, and then everything should be good to go. Okay, so that's it for everything we wanted to know about the law of sines, but we're afraid to ask. Next, going to be the law of cosines.